Okay, so it's a pleasure to introduce the next speaker of today, Francisco Gancedo, Paco, from University of Seville. So he's going to talk about local and global well-posedness in counter dynamics.
Okay, thank you for the introduction. First of all, I would like to thank the organizer for giving me this chance, this opportunity. It's a pleasure for me can give a talk in this very nice conference, online conference. So essentially, I'm gonna talk about Muscat and SQG patches or SQG chart fronts to counter dynamics problem. So first work I'm gonna talk about is Muscat. This paper, Global Well-Posedness for the One-Phase Muscat Problem. This is a joint work with Hongyi Dong and Hui, Huang and Wuyen. And second, I think I'm gonna have time to talk about well-posedness for SQG chart front with bounded curvature, and this is a joint work also with Hui and with Neil Patel. Okay. Very nice. So first slide, I would like to show you motivation. My motivation is going to be the 2D vortex patch problem. Okay, so I'm going, the 2D vortex patch problem, well-known classical problem, is considered to the Euler. Okay, incompressible fluid, and then here omega is the vorticity of the fluid, u is the velocity. We relate the velocity and the vorticity with the Biot-Savart law. And then when we put as an initial data, and then this equation conserves this property, is a patch solution, right? We have the vorticity concentrated in a domain. And the question, the kind of question we would like to solve is global regularity versus finite time blowout. Okay, so we start somehow with a regular boundary, free boundary, and we want to know if this regularity is preserved a long time. Okay, so for the vortex patch, this question is well understood by Chemin and by Bertocci and Constantin. They solve the problem in two different ways. In order to consider this question, I'm gonna move to more singular more singular problem, right? In trying to fight with singularities or global regularity. So first I'm going to consider the Muscat problem, okay? To have a picture about what I want to talk about. Is not the C, okay? Is the line that you see here, okay? Which gives you, this is the line, right? Between a moist region, you see moist sand, and then a dry region, dry sand. Okay, so we are going to have a fluid in a porous media, two fluids, or vacuum and fluid in a porous media, and we want to understand the evolution of this interface. Okay, good. So let me show you the questions. So we are going we are going to study incompressible flow. Conservation of mass, so very traditional or very classical equation. And then, because we are in a porous media, or let's think in sand, we are going to consider the classical Darcy's law. Okay, in Darcy's law, what we have is forces proportional to momentum instead of acceleration. Okay. So we have here mu is the viscosity of the fluid, u the velocity, p the pressure. I forgot this is conservation of mass, so this is the density of the fluid. So this here is the gravity. So we have gravity pointing down. Okay, I alleviate some notation with having permeability equal to 1 and gravity equal to 1. So this is just to alleviate some notation. So let's live in a planet with gravity equal to 1. Okay. Everything what I'm going to say is going to be the same. What is the Muscat problem? Well, the Muscat problem is when you consider the density and the viscosity and the density of the fluid having constant value in complementary domains. So we have two incompressible fluid which are immiscible. Okay, because we have this jump, so we are going to understand all this equation in a weak sense, and then we have to understand. We want to understand how move the boundary between these two domains. Okay, we want to understand if there is singularity or not. Okay, so for this equation, for this, all this classical equation can be reduced to an interface equation, so an equation for the contour, how it's moving. So if we consider, let's consider omega-2, the domain below, and it's going to be below a graph. Let's say, okay, so now we have xy in R2, the vector xy in R2, and then we have a domain which is below a graph. Okay, for f, it's going to be a periodic function. So let's consider periodic. You know, we have gravity pointing down, so this is a vertical domain in 2 dimensions. So we repeat periodically the interface. Okay. And then I'm gonna show you later. Now I prefer to give you the equation later very easily. I'm gonna deduce when we get into the proof of something. I prefer to deduce and then get into the into some points. The equation for f, partial derivative of f, is given by this operator, which is just the Dirichlet to Newman operator. I'm gonna show you later. Okay, here what I'm considering is the vacuum, as in the photo that I showed you. So vacuum fluid is on top. Okay, so we have viscosity of the top fluid equal to 0 and density of the top fluid equal to 0. Okay. Well, so because of the kernel of the Laplacian in this periodic in the horizontal direction setting, it is possible to write, and we are going to use this a lot along the talk, the Dirichlet to Newman operator in this form. Okay. So is this non-local operator in terms of f? Non-linear, sorry, also non-local, but non-linear operator in terms of f, a linear in terms of g. Okay. The g is implicit. So I'm putting here theta, and theta is related with g, with this also non-local term. Okay, so let me try to explain this to you a little bit. This is just a non-linear kernel. I mean, this is order 2 as x goes to x prime. Okay, this is order 1. So somehow this is a principal value singular integral operator applied to theta. Here there is a minus sign, so there is cancellation between this guy and please interrupt me anytime, okay? If you don't understand something and you want to ask. Here there is some cancellation, okay, if f is regular. So this is an operator of order 0, so we can invert this operator and get the derivative of g in terms of theta, okay? So let me simplify things a little bit. This is a mesh equation, and what I'm gonna do is just to linearize. So I'm gonna cancel out when I see a square somewhere, and then what we get at the linear level, maybe I can move. No, I cannot move. Okay, at the linear level, what we get is this this equation over here. Okay. Doing some trick with the sine and cosine, we find this operator at the linear level, which is just the Hilbert transform applied to one derivative, which is the lambda operator, the sigmund operator, 1/2 derivative. So going to the Fourier size, it is possible to solve this equation very easily with the Poisson kernel. And then what we find is just that when this quantity is positive, we are in the stable case. This is just when the fluid is below. Remember, we're considering one fluid. This is when the fluid is below. This is a stable case and very unstable a crisis situation, because this thing blows up and blows up even. Oh, this is the initial data, sorry. So there is no time here. Okay, this is the initial data, there is no time here. So when this is negative, this is very unstable, you put a very regular initial data and this doesn't make sense. Okay. Good. So this is at the linear level, the Muscat equation. This is a traditional problem from 1934, also studied by Safman and Taylor in 1958, considering experimental solution for the Muscat in a Hilly Shaw cell. It turned out that if you put a fluid between two plates and these plates are close enough together, the law to describe the dynamics of this thing is like Darcy's law. So you can compare fluids in Hilly Shaw with the Muscat problem. So lately there have been a lot of people. Okay, so there is a lot of classical results. I'm giving here like some of them, but more recent results, a lot of people jump into the problem. I'm plugging here like 60 authors just to show you the quantity of people that jump into the problem, because in terms of the dynamics, you can find very interesting dynamics, like global regularity for small data, like singularities. And I don't want to, I'm sorry, but I prefer to not go through one by one, because then it's going to take a lot of time. So for example, these are recent results, this year results, there are a lot too. So please allow me to, or let me, in order to give you an idea of what's going on, I'm gonna compare the situation that I already told you with one fluid. I'm going to compare this situation with the case of two fluids, Muscat with two fluids. So this is the equation. It's also a non-local equation, but let's say less non-local, right? Because there is just one non-local relation. Okay, and this is the counter equation for the case with of fluid with jump of densities. So we have two fluids with different densities. Okay, I'm going to talk about the stable situation, right? When there is no crazy behavior. So the denser, essentially the denser fluid is below. Okay, very good. So in order to summarize all the contribution of all the people, let me use this table. Okay, I'm going to compare the equation that I showed you at the very beginning, which is one fluid in the stable case, compared with the two fluid case, which is the equation that I show you, this equation over here. Okay. So considering subcritical spaces, critical is L infinity of the slope. It's a critical in terms of scaling. Okay. So L infinity of the slope, L infinity of one derivative is scaling variance. Okay. So the problem is well posed when you consider a lot of different type of subcritical spaces. When you have a small initial data, there is global assistance, even in critical situation. You are close to the linear case, okay? And then you have this parabolic behavior that I show you with the square root of the Laplacian, okay? In terms of singularity, it is not possible to have a square singularities, right? In which, for example, the two fluids and you have another fluid in the middle get close enough together and then you collapse along a line, for example, of two different level set. You cannot have this kind of situation for both cases. And the proof, in order to prove that, you use completely different approaches. But for example, in the case of one fluid, the case I'm going to talk about now, is pretty singular because you can have finite time splash singularities. So you can see two particles on a interface moving and getting closer and closer and collapse in finite time. So somehow you violate the incompressibility, right? Because you have two particles colliding. And for example, in the case of two fluid, you cannot have this kind of singularity. Okay, it is not possible to. The fact that you have a fluid in the middle does not allow the fluid to have this particle collision. On the other hand, for example, for the case of one fluid, you cannot have turning. If you start with a graph, you remain a graph all the time because there is a maximum principle. I'm going to show you now how to do this due to Wong Kim. There is a maximum principle, and then there is no turning. But in the two fluid case, it is possible to have turning situation. So you start with a graph, and then in finite time, you are not a graph anymore. This is important in this case because you enter in a stable situation, right? Because you start with the denser fluid below, you turn, then the denser fluid is above in some regions. So there is no, in the case of two fluid, there is no global system for large data. Okay, once you turn, you can have singularities. Okay, finite time singularities. It wasn't known if there is a global system for large data. And in the case of local system for critical data was recently solved for the case of two fluids. Okay, and it wasn't known for the case of one fluid. Okay, so what I'm gonna try to show you in this talk, what I'm gonna try to do is to remove these two questions. Okay, I'm gonna show you that there is global system for large data in a critical space. Okay. Good. So this is the theorem with Honji and Hui. So suppose that we have an initial data, which is Lipschitz, critical regularity. Then we have a solution, which is Lipschitz for all time. And we satisfy the equation in the L infinity L2 sense, which is classical for us, for which F0 is this initial data, and we have this maximum principle. And one interesting feature here is just that we have well-posedness, because the solution that we find are unique in its class. What we find is a viscosity solution. By viscosity solution is in the sense of Grandal-Lyon's viscosity solution for the Hamilton-Jacobi equation. Okay. And well, we are very happy with this result because this is the first construction of a unique global strong solution for the Muscat problem with initial data of arbitrary size in a critical space. Okay. And this is general result for any Lipschitz space. Very good. So, okay, I'm gonna try to give you some details and some ingredients about the proof of the result. Well, what's one difficulty, for example, for us, and I don't know how to solve, is high regularity. When you have high regularity, for example, you start with a very smooth initial data, so you can have short time system, and then it's easy to get the maximum principle that I told you for the Lipschitz norm. But at least for me, I don't know how to do it. It is difficult to propagate regularity. Okay. On the other hand, with low regularity, there are a lot of difficulties, which is to get the maximum principle, because now with less regularity, it's more difficult to prove this maximum principle. It is difficult even to satisfy the counter equation because you have to find a sense for it. And it is difficult to get the uniqueness also for the same, because we are in low regularity. But even though in this case, it seems that we have more difficulties, we are able to prove all these things, maximum principle, we satisfy the counter equation, and we are able to get the uniqueness. I'm going to show you some ingredient of the proof. Okay, so remember the equation that we already have are incompressibility. We have Darcy's law, okay, and because you know Darcy's law gives us just if we satisfy Darcy's law, what we have is an incompressible, an irrotational fluid. When this is satisfied where we have fluids, okay, where the fluid is, and then your velocity is potential. It's a potential velocity. So we have irrotational velocity, so we can write the velocity with a potential. So with this potential, we can integrate Darcy's law. Okay, we integrate Darcy's law. What is the equation for the potential? Is because it's divergent free the velocity, so it's harmonic, an harmonic potential. We want the physical, sorry, this is instead of omega f, this is omega t, the domain, omega 2, where we have the fluid. So we want physical situation, so we want the velocity in L2, finite energy, okay? And then at the free boundary, F is moving with time. This is our free boundary. We go here, okay? And then we put this at X fx. The pressure is 0 because on the other side we have vacuum, okay? So there is no surface tension. So the condition for the pressure is 0. And then what we have is the profile, right? This is the Y equation, so we get fx. And here you see, no, the evolution of F is given by the normal direction of the velocity because it's moving with the flow. And here you see the Dirichlet to Neumann operator, right? The normal derivative of phi, okay? And here is where the Dirichlet to Neumann operator appear, right? This F came from this profile, and then here for the free boundary, and then these quantities from the value, the harmonic extension or the harmonic potential. Okay, very good. So because we have harmonic functions, and suppose that we have two profiles which are Lipschitz, okay, periodic Lipschitz, and then C11 at one point x0. Okay, C11 for us is just we squeeze the function with two parabolas, one from above and another one from below. Okay. And if f1 is less than or equal to f2, then we have this order for the Dirichlet to Neumann map. Why? Why? This is just a maximum principle for a harmonic function of, you wish, the Hopf lemma. We are using the Hopf lemma, and then we get this order. This was this was well known. Having this property, if we have two solutions that evolve with the Dirichlet to Neumann map, and if initially there is an order, then we have an order for all time. These are regular solutions, okay? So there are orders for all time. This is a maximum principle which can be proved with the usual argument. Assuming the opposite, then you get an easy contradiction. With this property, then I can do this maximum principle for these two functions, plugging y as a parameter, right? But this is what is telling us that if initially we are Lipschitz, then Lipschitz is propagating for all time. And this is the W1 infinity maximum principle that I already told you. Okay? Good. Now we want to get the result in the critical case. So what we are going to do is to regularize the system. This is a usual trick, but we have to regularize it in a way that we still conserve our maximum principle, right? We not screw too much the structure of the equation. And then the usual way is to regularize with in classical PDE theory, no, with the Laplacian, right? This is good for our maximum principle because we are going to keep it right? Because of the property of the Dirichlet to Neumann map. But somehow for Muscat, when I have to regularize, usually I use more. I need more, or I regularize the nonlinearity, or I put more dissipation. So here we have to handle with this thing just to keep our maximum principal for the regularized system, and also we regularize the initial data, right? And then use some theory. And well, we were able to prove global intent system for this regularized system. One of the main reason is because we got a new inequality. We got a new inequality for the Dirichlet to Neumann map, the L2 norm. This bound was known, but what was not known was how depend this bound of the profile. We found an explicit dependence of the profile F, okay, to control the L2 norm. The Dirichlet to Neumann map is like one derivative function, okay, for Lipschitz profiles, okay. And well, this is important because we are in dynamics, okay. This bound wasn't enough for us to prove our theorem because there is dynamic, this is moving, so we need to know how this is a universal constant, right? How this thing is moving. Okay, so thanks to this inequality and another trick, low frequency, high frequency, some trick, we are able to prove global system for this. Now what we want to have a system is to take epsilon to 0. Okay. Okay, this is linear. We have a maximum principal for a regularized system. This is linear, this is gonna go well. This is linear, this is gonna go well. And remember that if you believe me, the way in which I represent the Dirichlet to Neumann map with explicit kernels, having this cosine, hyperbolic cosine, and sine, etc. The nonlinearities, the two nonlinear terms, they both are are derivative of something. Because they are derivative of something, I can put a test function, integrate by parts, and then I can forget about the derivative, and what I have to do is to have convergence for this guy, okay? For theta is derivative, is at the level of derivative of f, we have weak convergence, but for f, we have a strong convergence, okay? Even though here we have singularity, this function our tangent is bounded, so if we forget about this derivative, here we have somehow a strong convergence, here we have weak convergence, and then this converges. Okay. Here, if we get the other nonlinear part, the part in the evolving equation with the time derivative, we can remove this x derivative. We find this guy over here, which is still singular. Okay, but doing some tricks, we can find this thing like a Hilbert transform, which is linear, and then it's okay with convergence. I mean, Hilbert of f epsilon, and for f epsilon we have a strong convergence. Remember that f is in W1 infinite uniformly. Okay, so we have a strong convergence for f, and then we convergence for theta epsilon, and then we are able to pass to the limit. Okay, and then somehow we have the systems result. Okay, these are the tricks I wanted to show you. And now uniqueness. I'm not sure if you're familiar with viscosity solution, thinking in Crandall-Leon theory for Hamilton-Jacobi. And remember that this is the way we find our solution, right? Because we regularize with the Laplacian, we have a small viscosity of order epsilon, and then we take epsilon to 0. So what we want is to find that the solution that we get are viscosity solutions, and then use the theory to get the uniqueness. Okay, even though this theory sometimes is used to get very weak solutions, here we satisfy the equation point-wise. So it's some machinery for us to get uniqueness. Good. So what is a viscosity solution or subsolution? If f is upper semi-continuous, if you worry about this upper semi-continuity thing in continuity, this is just to to fit in what we need. And then we consider any test function, which is regular, continuous, and then is C11. And then if f minus phi have a global maximum in this interval, then phi had to satisfy our equation with an inequality. Okay, it's on top, and then we have the inequality. For a super solution, we change with all the thing that you see in bracket. Okay, we need for f also continuous, if you wish, or lower semi-continuous. We need a maximum for f minus c, and then we have the other inequality. A viscosity solution has to be both sub-solution and a super solution. Okay, very good. So well, we have to prove a consistency argument that says that if we have a sub-solution and at the end of the day our solution is regular enough, so suppose that it's Lipschitz and it's C11 at one point, just at one point, sub-solution, then we satisfy the equation, the inequality, not the test function, also the function. Okay, we have to prove this consistency. This is the proof of this is pretty technical, but just let me show you that we need strongly this result, elliptic result that it was hard for us to prove for some time, but using elliptic theory at the end is possible. So suppose that you have a function which is Lipschitz and is C11 just at one point, then its harmonic extension is Helder of order 1 plus alpha for some alpha, whatever alpha is good. And this M is a good constant that does not depend on the domain, does not depend, just depend on the alpha, on things, but not on F. It's uniform in F. Okay. Okay, good. So with this consistency, at the end, using some technique of this viscosity subsolution and viscosity subsolution, at the end, we are able to find a comparison principle for the solution that we get with the system. Okay. So if F is a subsolution and G is a super solution, viscosity solution, if initially we can compare one with the other, then this comparison remains for all time. So this is what gives us uniqueness, right? Because the solution that we find are sub-solution or super solution, okay, and then we can compare them. If they have the initial data, I can put one from below and one from above, and then at the end they are the same. So they are unique with this comparison principle. Okay, and the technique of this is not new. We use sub and inf convolution, but the important thing is the consistency argument that we already proved. Okay, I hope more or less you see a glance of what we did for this result. And now I'm going to move to another counter dynamics, but now what I'm going to consider is SQG sharp temperature front. Okay. So now instead of thinking in a fluid filtrating in a porous media, I'm going to consider SQG, which is two-dimensional surface SQG give us solution of a three-dimensional SQG, three-dimensional SQG equation that consider strongly Coriolis force for high big masses of air, of water in Earth, right? Rotating Earth. Okay. So think more in a picture, beautiful picture like this. Okay, so SQG equation was introduced in the mathematical world by Konstantin Maida and Tabak. But what I'm going to consider here is the patch problem, okay, for SQG. So theta gives us the temperature of the fluid for SQG, and theta is going to be a patch, as I'm considering here. There is a bounded domain, but the relation if we compare with the 2D vortex patch, it's more complicated, it's more singular. Okay, we have incompressibility with the perpendicular gradient, but instead of integrate twice with the Laplacian, we integrate once. Okay, this is the risk potential. Okay, good. Some properties we are considering finite energy, and also, of course, we are in 2D, so the area of the domain is conserved. Okay, so some people introduce the generalized SQG patches equation in which you can interpolate between 2D Euler and SQG, and you can even do it more singular. So you move a parameter. If alpha goes to 0, alpha equal to 0, we integrate here twice, and then we have, this is Biot-Savart law, so we have 2D vortex patches. Okay, so I show you in the first slide. If alpha is equal to 1 is SQG, between 0 and 1, you are in the middle in terms of singularity. For alpha between 1 and 2, you are more singular than SQG. Okay, and the people work a lot. So alpha equal to 0 vortex patch, alpha equal to 1 SQG, chart from. Okay, in any case, we always can reduce this equation to this one, which is an equation for the contour. Now this is now we are not considering a graph anymore. This is a closed contour, periodic closed contour. Okay, and this is the equation, the non-local equation that we are considering. Okay, that give the solution of this transport equation. Okay, so let me linearize to see more or less what's going on. So the linear equation is in term, the evolution linear equation is in terms of this linear operator that the Fourier size is given by this. So here we don't find an hyperbolic, a parabolic equation. It's more like a wave equation, or you wish a dispersive equation. Okay, because of, you have the symbol I here. Okay, if you go to the Fourier side, and then you can integrate very easily, you find a dispersive equation. Okay, so let me show you some previous results. I'm going to summarize a little bit, but now I can go one by one because there is not that quantity of literature. So the contour dynamic formulation was first found by Resnick in his thesis. Local system was first shown by Rodrigo using Nash-Moser iteration theorem with infinity patches. I was able to remove the regularity and do it in Sobolev spaces. And then together with Dongo, Peter, Diego, and Yahong, we were able to do the more singular case, okay, when you are more singular than SQG. It is one very interesting thing about getting local system in Sobolev spaces, just that there are numerical simulations showing clearly numerical blow up. Okay, so Diego, Marco, Ana, and Jose Luis were able to show some numerical simulation showing blows up. I'm going to show you a draw. And also recently a different simulation due to Scott and Richler. They both have different situation, but they show like curvature blows up in finite time. For the patches, they start to move in different ways, but at the end, they see that the curvature has to blow up. Okay, so for example, the first group of people simulation, they consider a hot patch, a cold patch. They start to spin, getting close together, and then at these 2 points, they see how the curvature blows up in finite time at the same time that the particle collide, okay, with the other patch. Okay. Okay, so together with Bob, we were able to prove kind of what happened in this situation, that if we control curvature for the patch, then you cannot have point-wise collision. Okay, this point-wise collision, if you control the curvature, is not possible. there are some geometric results in which you have patches changing convexity from being convex to non-convex result. And also there have been recent results in which people find global in-time solution, rotating solution. There are a smooth solution, C infinity, or even analytic, rotating uniformly in the different cases. Okay, in different cases with different geometries. Even more, Javi was able to prove stationary solution, not trivial geometry. The circle is a trivial geometry, well known, but the stationary solution, there are other not trivial geometry which are also stationary solutions. I have 10 minutes or around 10 minutes.
So actually I have 5 minutes and 5 minutes for the questions.
Okay, 5 minutes. I think I can make it in 5 minutes. Thank you. Okay, so there are global systems for small data in near planar situation using these dispersive properties. Okay. Uniqueness. So weak solution can not be unique, right? So, but if you consider front, they are unique. Okay, we were able to prove that for SQG. And also there are finite time blow up situation when you consider fixed boundary. So in the upper half plane, if the patch touches the fixed boundary, this is a very singular situation where the patch touched the boundary. Sasha, Lenia, Zhao, and Andre could prove finite time blow up, a system of finite time blow up for alpha between 0 and 1/2. And what's interesting here is just that the same situation for the bottom patch, there is global existence, there is no blow up. And then together with Neil, we were able to extend this situation for more alpha, so extending the very short list of blow up for incompressible situations, okay? Also, we are able to find a blow up criteria with Neil, controlling essentially the C1 plus delta norm. So this is interesting because it's less than curvature. And in the numerical situation, the people find curvature. So if you have regular solution, if you control somehow this norm and then the Arcor condition, then it is okay. Good. What we were able to prove with, oh, I forgot. This is a joint theorem with Hui, Huang and Nguyen, and with at Maryland and with Neil Patel now at ICMAT. So we were able to prove, and for us this is very interesting, is just well-posness with unbounded curvature. Okay, so all the global situation that I told you needs a lot of regularity, and curvature was crucial in all the numerical blows up, right? Curvature was blowing up. So we thought that it is interesting to have a well-posness theory and to construct patches with unbounded curvature. This is for SQG. Okay, so essentially we use Sobolev spaces, and the space is H2 plus S, thing in S very, very small, so we allow unbounded curvature. Okay, and this is the question we have to solve. We have some tangential term to have some cancellation. So very quick, in 2 minutes, I'm gonna show you some tricks of this proof, okay? So the tangential term that we add, this is for the contour dynamic, this is okay, because what we care is about the normal direction, give us this relation. So somehow the tangent vector only depends on time. So if you take one derivative of the tangent vector, you get this quantity, which is 0. This is known. This was known and it was used for other theorem. Also, we have this relation. For a function, this doesn't have to be true, this identity, but we have a curve with tangent vector that only depend on time. So this gives cancellation. This cancellation is order 1. Here we have cancellation order 2. This was also already used. But now the new things is just that we have to find new tricks to control different terms because we are dealing with fractional dissipation. In particular, the lambda, the term that give us these two cancellation, is pretty singular, and it was easy to handle with 3 derivatives, 4 derivatives, 5 derivatives. But with fractional derivative, this was pretty singular, and we suffer to control like in commutators and things like that. The hardcore condition also need a new tricks, like doing a smart decomposition in low and high frequency. And finally, we need a new trick for uniqueness. So for all the things that we need to control, like a Sobolev norm, hardcore condition, and uniqueness, we need a new trick. 2L2 is not enough. At least I don't know how to do it. It's not enough. If you go to H1, I mean, in L2, you consider the difference between 2 solutions. You check the evolution of the L2, it seems that you need more regularity. You go to H1, it seems that you need more regularity. You go to H2, it's too much, because the regularity that we have is H2 plus a little bit. If you go to fractional derivative, it's a mess. I don't know how to handle, because there is no parabolicity, there is no. The trick was to consider the H1 of the difference between 2 solutions, and then the difference between the length, because the length is constant, and somehow it's like L infinity of 1 derivative. And with this new trick, we were able to prove uniqueness. Thank you very much for your attention.
Thank you very much, Paco, for the talk. So as you all know, so if you have questions, you can either open your mic or write on the chat or raise your hand. So are there questions or remarks?
I have a quick question.
Mm-hmm.
Yeah.
So Paco, let's go back to the Muscat problem.
Yeah.
Let's go back to the parabolic bound on the harmonic extension. So the bound for a function that's Lipschitz and C11 at one point, the one that's parabolic, that
Yeah.
one. So this is a very delicate point, because it's an elliptic regularity problem, but you have things depending on time. You said that M does not depend on F.
We know that is uniform in F. So
wait.
Sorry.
Okay. So you have the condition with X naught. Is X naught fixed through the evolution?
With X
Yeah, X0, right? You have it's not only at W1 infinity. You have an information that you are using, that you have
I think
in parabolas.
Yeah. I think so.
Doesn't that also enter in the alpha?
No, I don't think so. I think that because it's fixed, we don't have problem with that.
If it is fixed throughout the evolution, then probably you're not. So essentially what happens, and this is a general worry that I have, whenever you do elliptic techniques in evolution equations, they work for compact subsets of functions, but you are in a weak situation in which your sequence of functions or the time-depending functions are not necessarily compact in the space that you are looking at. And therefore, you invalidate all these, essentially de Giorgi kind of things. So you have to always be careful that you are in a situation that stays compact in this elliptic thing. So that's why the question is, if X0 is not moving, I think that in general, these alphas depend on the solution. They don't depend only, they depend on the situation at hand in some sense, and depend on the solution, even if they don't depend, they depend uniformly on F, but they depend on the solution structure. So that was my worry about this X naught. If the X naught was moving, then all of a sudden you have a problem, or you potentially have a problem.
Yeah. Actually, this was the last point. I mean, this was the last thing that we needed to have the theorem. So we were very, very, very careful of this point. Because we are using this sub-solution as super solution, we have a parabola from above, from below, and then you think you have the parabola move, but move not too much, because this is the uniform thing that we have, and then you put a circle inside.
Yeah, yeah.
And then we need this uniform thing using Poisson kernel on the circle which is inside the parabola. And then very, very carefully, we compute this, because here F is gonna be moving because we are approaching with sub-solutions to our limit. So this F is gonna moving, the point now, the phi is moving, and then we control uniformly this constant. And then this gives us the result. So I'm pretty sure that this worked because this was the crucial step, the final thing we had to prove to have the theorem. And then we very, very, very carefully check that everything was under control.
All right. Okay.
Thank you so much for the question.
Yeah. Okay. All right. Thank you.
Okay. Are there other questions or comments?
I think Gabriela and Anna raised their hand.
Oh, okay. Sorry, I was not seeing.
No, I don't.
Sorry. Thank you for clapping.
Okay, so let us clap again and thank the speaker. Thank you, Paco.
Thank you.
And yeah, we will resume at 1:10 So in 1 hour, so we are going to have one hour break now for lunch.